I think it's time to start. Okay, I understand. I see only 28 something people, so some people start later. In any case, I think two things. First of all, before I come to your question, I understand that there were a number of questions about this particular homework. And so I want to extend it until this coming weekend because I want everyone to solve it. It's not just that I want to collect the homework and grade it. I want you to solve this homework because I know it has some challenges, but it's important to address those and try to solve it, all right, fully. So I will send a note, and I need to make a point here, send a note that is going to be extended until end of Sunday. Okay, having said that, before I ask for your questions in this homework, I want to say one thing. I see a lot of people who are trying to solve the problem, the homework, in the last day, and in fact, many in the last evening. And that's not helping anybody because this is not an easy homework. I mean, it's not conceptually difficult. However, it has these small things, all right, that you will need to address, and it takes time. And also, if you want to ask me questions, it comes down to whatever the last day, the last few hours. And it's not productive, neither for you or for me, because I get also stressed out. If you are in the last few hours and you are asking for help and it's late at night also. So having said that, now it's the end of the class, but I would like to suggest that don't leave homework that is complex for the last minute. You're not learning much, you're under stress. Very few people learn. You can only perform under stress well if you have already done your work ahead of time, and if you are, say, in a final or in midterm, in an exam, in a presentation. But trying to prepare yourself for that, it takes time and effort, and you need to give yourself enough time to learn the material. That's number one comment. Number two, I told you, I believe I told everybody, and I will repeat it again. I'm putting together, not this one, not this document, that the title for this document is a design of an LNA as an example, but specifically what I have created, which is a review on LNA. This review, what I'm trying to do is to put together all of the material and all of the equations. Now, one thing I told you last time, and I will repeat it here. There are a number of equations, and it is possible that at some point I may have made a typo. So instead of printing the right numbers or 1, 2, since there are lots of scattering parameters, I may have made a mistake. So you have, I asked you that last time, take that. I mean, of course, I would like to have it perfect, and I would appreciate those who will tell me any typos that you find. There was one, as a matter of fact, typo that one student got really conflicted about, and I don't remember where it was exactly, this one. But in any case, I think it was the previous one. I corrected it. So when I write my notes, and maybe it was it in this one? There was one equation in one of these where the K we had included in the denominator. I had made a typo. And this student, and the student who had that problem, of course, was trying to figure it out the last, like yesterday night. And it was very frustrating for the person, obviously. But I just want you to understand that while I'm doing this, I'm putting my notes together to help you. You also need to be careful when you read my notes. You know, I'm a human being. Here, that was equation 3. I had in the denominator of K2, and then magnitude of S12, and I had S22 or S11 something instead of S21. All right, so please, especially the review, because I'm collecting equations from everywhere, and I try to put it together to help you check the equations. So that's number 1. And number 2, okay, so the last one, let's go to the specific questions you had about how you draw the various circles and how you accommodate the cases where the center of your circle is very far away from the Smith chart. And so I'm gonna go, this is the approach for design for an LNA, all right? So I have corrected this and I have placed it and I say new. So in the new, make sure that for those who have downloaded this on Monday, you download the new one because I have corrected the typo. Okay, so let's go and explain. And I have also uploaded this because we did an example in the afternoon during office hours. In this one, where I'm going to go is to circles like this. Okay. I will add a page. I will, yes.
I don't know if you're meaning to, but you're not sharing anything.
Oh, okay. All right. Yeah. No, I did not mean that, unfortunately. Okay. So one thing that I wanted to say, maybe that's what I need to show you. In this document that I put together that is called Review of an LNA Design, there was a typo here. There was a typo there. I had S22 or S11 instead of S21. So I'm saying because there, and I'm augmenting this, I have added sections today. So now it's down to page 18, 17. Please, while I'm putting everything together for the LNA, because I know it's formulas everywhere in the book and the back and forth and it's conflicting. So I have it there because I would like to use this material, go down and review the steps. The steps are extremely important, but check the equations, please. I will give points to everybody who, I'll give up to 100 points to people who will find any errors I have in this equation and send them to me. And the reason I do that is because it's important. I take it as my responsibility if there are any typos or any other errors, all right? It's not your problem, it's mine. So if you check these formulas, as I would like you to do always, since I'm writing them by myself, and if you tell me what the errors are, I'll give you extra points. Up to 100 points. For every error you find, I'll give you about 10 points. All right. So about maybe 10 possible errors. I don't think I will have more than that. All right. So that is what now you see. Going back to your question, I had a lot of questions yesterday from individuals who have been a little bothered by the following. Do this paste. Okay, and I will write here just as an example. So let me put here examples. So you know that is not the solution of the previous problem. Okay. All right, so in this one, you remember when we either find stability, and usually for stability primarily. Is that also the Zahin? Was it in in the stability circle where you got this data, or was it in anything else?
Oh, are you talking about the gain?
It was in the gain that you got this data?
Yeah, because I was sending for the GP.
So it was GP. Okay, fine. We'll take it one at a time. Let's talk about stability. You remember first, we have circles for stability. We have circles for gain. We have circles for noise. And we have circles for VSWR. So there are 4 different types of circles. So 4 types of circles. All right, so it's stability, it's gain, it is noise, and it's VSWR. All right, and for all of these types of circles, we have the center and we have the radius. All right, now the formulas, they are included here. So for example, when I look at these are the VSWR circles. When I look at these, the same input VSWR circles. And then when I look at these are stability on the front, CLRL, on the back, CSRS, and the noise. I should have the noise circles somewhere. Let me see. On the side, I don't want to bring them forward before. Here, 1 second. CPRP. Have somewhere the noise circles, which are also given by the R, the C, or the center, CF, and RF. But let me see where I have them. I'm trying to figure them out. Constant VSWR is this one. Okay, here. So you have the constant noise circles. And then here. And then we got the gain circles, and I told you about the gain that we are going to use one combined expression, GP and RP. And let me find those from my notes here on the side. Here. So, and these are the ones for GP and RP. Okay. Now, what happens with all of these circles is that you have to find, and that's where we are going now to the example. Okay, so you use these circles, the whatever appropriate formulas you have, and then you find a center, and then you find a radius. So let me try different examples. Let's assume that you want to look. Let me start with stability. Okay, in stability circles, so practically when I take this one and I go here, we find circles on the front end, which is CS, and a radius RS, and on the back end, which is CL and RL. From these circles, you find gamma S. From these circles, you find gamma L. All right, practically. But what happens, you don't necessarily find them with stability. We just find regions where it is stable. So let's assume that R sub S, C sub S and R sub S came out to be the following. So CS is 4.5 and RS equals 4.7. Okay, for example. The same thing applies on the CL side, on the load side. So in this case, 4.5 is totally away of my Smith chart, because normally I look at this scale to find the magnitude. The Smith chart always has a radius of 1. So this scale goes from 0 to 1. When it is 4 or something, obviously, it goes very far away. Now, one more thing that I forgot here is that CS also has a phase. Let me give you some phase here. Let's assume that the phase is 75. Okay, so phase 75 degrees. First of all, I need to find the phase, because it tells me that all of the centers are on one line, and this line has a phase of 75, and I'm looking for a phase up here. On this one, that gives the angle of reflection coefficient, okay? And I find 75. 75 is 2, 4, somewhere here. And then I draw this line. Okay, and then I find that this is the line where all of the circles, the CS circles, will have their centers. Okay, that line. One other thing I wanted to tell you, to remember for you, when I do those things, you can see I do it from Notability, and I import a Smith chart. I don't have a compass and I don't have a ruler, so my values, the way they are depicted on the Smith chart, are approximate. So keep it in mind, all right? For you, if you do it on paper, you have a ruler and you have a compass, then you can do it much more accurately. Okay, now let me go to this one. This C sub S is 4.5 here. 4.5 is totally away of the Smith chart, because usually I measure it from the center, all right? This magnitude of 3.5 is going to be measured from the center of the Smith chart going outwards this way. So obviously, if this distance here, from here there is 1, then 4 is very far out. So I keep that in mind. Then I'm looking at my radius, which is 4.7. That means that if I had a circle like this, so now assume that to visualize, assume that your Smith chart was this small. You make it very small, all right? And then I put here the center of the Smith chart. And now along this 70-degree line, I can go 4 times. So it's 1, 2, 3, 4, say 5.5. I will 4.5. I will be somewhere here. That will be the center of this circle. Okay. Then how much is the radius? If I were to even make this smaller, all right, so I could draw the radius here. Let's make it smaller. Then my radius would have been from CS, I will draw a circle that has 4.7. From CS to the center here is 4.5. So the radius is going to be somewhere here, and the circle is going to be this one. Okay, something like this. Now, since I cannot do this all the time, I cannot make, because some other times it might be 300, you know, I mean, it depends on the scattering parameters that they have given us for the transistor. This center, this CS point could be much further out, so it does not make sense, you know, to try to draw it. So what do? We say, okay, now that I have done this, if I increase it a lot, and if I come here, at this point, practically the line that I see, and I will do it with red, another one, blue. So the line, this green line that goes through the circle, I can assume here that it's a straight line. In fact, look, I'm trying to do a straight line and it goes directly up there. So practically, I could remove this green line, and then I'm left with a straight blue line, which is not a bad assumption if I am increasing my Smith chart. So practically what it tells me is that my circle most probably is gonna come like this, but I can draw a straight line. And in fact, the straight line was somewhere different, was not exactly there. Let me be careful, 1 second. Sorry. Okay. All right, sorry, I have to do the, I have to do this. Well, the blue line was not exactly through the center, right? It was like this. Where this distance here between this straight line and this point was 0.2, because up to here was 4.5, and up to here, up to this line, was 4.7. So the difference between these two is 0.2. So I erase the rest. As I said, I erase this, and practically I leave, that was my original Smith chart, I leave the straight line. Okay, having said that now, all right, so this one, if you remember, okay, this one was going like this. All right, so now if I take all of this that I've discussed here, then what I can do is see exactly from this how much is 0.2, and 0.2, which is the difference between the radius and the distance of the center of the circle from the center of the Smith chart, 0.2. I can go here by a 0.2 distance, and then I can draw a straight line like this. And if I place it right, perpendicularly, this is gonna show me exactly where the circle is. And if I want it, in fact, so I can say, for this particular case, if my S22 is less than 1 for the input circle, so I can say that this is my stability region. Okay?
Can you explain that last step again? The one with the horizontal line?
Okay. Let me go to this one. When I create a circle, a large circle that goes through the point CS and has a radius of 4.7, the circle is gonna look, let me do the circle blue, since I used the blue. It's gonna look like this. Do you agree? Whatever.
Yes.
Yeah, okay. Cut that one. I need to create a circle. Okay, so if I increase the shape, practically this side, this part of the circle from A to B looks like a straight line. Do you agree with that? If it's not exactly straight, it's going to be very close to a straight line.
Mm-hmm. Yeah.
Okay. Now, therefore, so and this distance is 4.5. This distance is 4.7. What is the difference between 4.5 and 4.7? It's 0.2, which tells me that this distance here, the one that I draw with red, is 0.2. Tells me that this is 0.2. All right? Yes or no?
Yes.
Okay.
Yes.
Now, okay, now then I'm going here, and since I cannot go and put the real center of the chart, I'm extending this brown line, which is the axis on which CISA base is. I'm drawing a straight line which has to be perpendicular here, all right? Because the circle, my circle would look something like this. All right? And if S22 is less than 1, which is what we've seen for stability, then the brown region is where your stability region is. And that's where, this is from that region where you can select your gamma S. If S22 were to be higher than 1, it would have been the other side of the Smith chart. But usually S22, it's always S11, S22, in, what did I say? 99% of the cases is less than 1 that you're gonna see. So that's your stability region for that case. Any questions about this? Yes or no?
Yes, the stability region should be on the side of the phasor angle, right?
To be on what side?
The side of the phasor angle.
No, this is for CISA base, the angle, not for the radius. When S22 is less than 1, then it is the intersection between the Smith chart and the circle of stability, but the outside part of it, not inside the circle.
So when
outside of the circle.
You mean like when the RS is smaller than CS, then it's on the other side, right?
When it's smaller, it was gonna go somewhere here. Let me see. Blue. The circle, it was gonna go somewhere there. And if it's too small that it goes outside, it was gonna go somewhere there. And then in that case, if S22 is less than 1, then it's all of your Smith chart. Is any questions about this? Any questions? Okay, now with that, I will erase what I did here so we can ask the address the other question you have, Zayhin. So what did you say that you found?
Yeah, I found that for the circle of the GT, it is, or GP, it is not possible to draw because because C is very large, and the difference of the absolute value of the difference of R and C is over 1.
What a sec. Let me find these expressions for the circle. Okay, I will go now to the other one. 1 second to solve this problem. Copy. Okay, let's go here.
Okay, by the way, so the gamma S is the output stability region, right? Or the input one.
Do you see here? Here it says that if your S22 if you are on the gamma S plane and your S22 is less than 1, your stability is on the Smith chart, but outside of your circle. Outside.
Yeah, but in the homework, it's not given with the VSWR. Instead, it gives a
It's
GP.
not a VSWR. Don't look at this VSWR. This VSWR is what I found when I tried to print this circle and find the CS. This is not the constant VSWR circle. It's a VSW. It's how I did this the way to show you how to find CS. So let's go back to your question. Your question was that you used C sub. Let me see.
Yes, the gain.
1 second. Okay, you said that you used that one and you found that your C sub P was extremely large.
Yeah, it's like 3 or something, but the RP is less than 1.
Did anybody else find the same result?
I did as well. I got stuck.
So you
I got the
found that, okay.
I got the exact samization, like exactly what
Okay.
he's saying.
Okay, so practically what that tells you is the following. Add page. All right, let me add here. All right, so you found that your C sub P, let me make this as small as I can. How about if I do this like that? Okay, you found that your C sub P, how did you find this? You took C, you varied the values for G sub P, and then you found.
Yeah, GP is small GP is big GP over S21 squared. Yeah, and
right.
Yeah, when the GP is equals to GT,
what value for GP did you use?
10 dB, which is 10.
Okay, 10. So you used 10 and you found GP to be very large.
Right.
Okay. How much did you find your S22 square minus delta square?
Wait, I didn't say GP is very large. I said CP is very large.
No, I understand. I'm trying to, how much was your GP?
My small GP?
Mm-hmm.
It's 1.1111 something because S21 is 3.
Okay, so you got a smaller value. Okay. And how much was your S22 minus S22 square minus delta square?
My delta, let me check with you.
It's like really close to 0.
It's very close to 0. So practically it gives, and how much was your C2 complex conjugate, which I don't have here. I have to add it from your previous.
Are you talking about the C2?
Yes.
Which is C2? C22. Hold on. Which is C2, please? Which C2 are you referring to? Because
okay, wait a second. Wait, I need to find the equations. C2 is a value that is given by S22 minus delta S11 complex conjugate. It's not here, but we have it on the previous.
I think it's not that one. Let me check with it.
But in any case, so there were so the two of you found. So here I will address your question. The two of you found that your C sub P is very large and your R sub P is much smaller, which practically, if that's the case, all right, if you found this, that tells you that your CISA-P, and what is the phase of CISA-P? By the way?
CISA-P is negative 80.9 something.
80 something?
Right, negative 80.
Okay, so it's gonna be down here.
Okay, what GP? Hold on. What CP are you? What C2 are you talking about? Is it S21
Forget
minus?
about that. No, forget about this. Just give me the CP. We're not gonna go yet because we are gonna take a long time. So it was about your CP was like minus 90 degrees.
Minus
So
80 point. Minus 80.9576.
Okay, so it was something. Oops, it was
Almost
down
90.
here.
Almost negative 81.
Okay, so it was down there. So we'll move the Smith chart here. Okay, somewhere there. And we'll try now to draw it approximately. So your CP, the center, would be somewhere here. Okay, somewhere there.
Right.
And your RP, how much was it?
0.75.
So
yeah,
practically,
0.575 something.
it's very interesting because practically that tells you, let me see, that if these are correct values, it tells you that your circle is here. So practically that tells you that you don't have any point of the Smith chart that gives you 10 dBs.
Right.
So you have to go to a lower gain to be able. So this, which is surprising if S21 is so high. S21 is 3, isn't it?
Yeah.
If S21 is 3, why do you have this low gain? I mean, why to be able to go here somewhere or something like that to start intersecting? That means that you have to go to a much lower gain than 10 dBs.
Yeah.
Okay, let me ask, who else had the same problem with GSAP?
Professor, I got the same radius, but not the same center. My center makes it so that the circle goes within the Smith chart.
So where was your center?
My center is at, I have the Cartesian coordinates. It's at,
yes.
It's in the first quadrant. It's 0.2679 plus 0.82 J.
Yeah, it's first quadrant is somewhere here, say. How much, but I need the phase in this one to be able to tell you.
I can get to the phase real quick. The center is, or the distance is 0.87.
0.87.
Yeah, that's the distance from the center of the Smith chart.
Okay, somewhere here.
The phase, I think, is 72 degrees.
Okay. Okay, let me raise that. 72 is on the other side. 72 is going to be here. So it's going to be approximately. It's going to be somewhere there.
No, it's on it's in the first quadrant.
There's no 72 in the first quadrant. The phase, that's why you have to look at the phase is different. See, this is not a traditional, this is the Smith chart. It's not like an XY. So, so I was wrong when I said first quadrant. You have to go and find magnitude and phase to be able to predict, because the phase here starts at 0 and goes here to 180.
If he's looking at the wrong degree scaling, he could be talking about like 35 degrees or 36 degrees, somewhere around there.
I'm sorry, I do. Yes, you're absolutely correct, and thank you. So 75 is here. Okay, good. There. All right.
Yeah, that's.
I apologize. Yeah, I got confused for a moment. All right, so here, somewhere there. And how much was your radius?
0.87. I'm not sure if that's right because I thought it was outside the Smith chart. So I'm gonna check real quick.
Okay.
Dr. Katei, I think I
Yes.
know what the problem was. So when you had the value of GP in the notes, like from the
Yes.
previous class, I believe that it's different than the equation you gave for how you found, or the CP, I mean.
Okay, let me see. 1 second. So
Might be
CP, I'm going
different.
to the next one. Yeah. Let's see.
Look at C2. Yeah, it is, because on there you put CP as S21 minus delta S11 complex conjugate, and C2 is defined as S22 minus delta times the conjugate of S11.
Yeah, let me find it 1 second.
It's on.
Which page is it? Down south.
It's on the.
This one.
Yeah, that formula right there. So when you said in your other notes, you say CP is equal to lowercase g sub p times C2, the conjugate of C2, right?
Yeah, that's C2 here.
But C2 is defined as S22 minus delta S11
Okay.
complex
Just a
conjugate.
second. Yes,
And
yes. So there was a mistake here.
And when I just changed my code to S22 there, or like I changed it, it ended up, it's inside the Smith chart now, and it's the same angle that whoever was talking about it previously was saying.
Yes, see, exactly. C2 to S22 minus delta S11 complex conjugate, right? Okay, well, I apologize for my errors for those of you. Where did you find this formula yourself?
Me?
No, I'm talking to the other student who just spoke. Who was the other student who just corrected, found that error? You got to get, you got some points. No, seriously, I mean, that is, it bothers me that they had that there. Okay. So, could you tell me a little bit where you found that formula?
Me?
That C2 is S22 minus delta S11 squared.
Oh yeah, so that formula you gave back a long time ago, like when we were just talking about normal designs. So that was in.
Okay.
All right, let me see if I can find the actual set.
No, but it is in the book. Yeah, the book, it does not have it as C2, but it does show that it's S22 minus delta S11.
Yeah.
And yes, it shows that. Let me also.
Oh, it's in the. Let's see, what notes was it? When you did you did like a maximum gain. It's like the value you find when you're doing like the maximum gain.
Maximum gain. Yes. Was it correct there?
Yeah, it's correct there.
Yeah. Okay. No, it was a typo here. I'm sorry. I apologize for that. Okay.
Yeah,
so that should solve the problem and then should bring the circle into the Smith chart. And then how about R sub P has the correct value, isn't it? What you found. It was the C sub P one that went crazy. Yeah.
Yeah, now it's a lot better. It works out.
Yeah. Okay, so that's please go for those of you who had problems with this and fix it. You're gonna help. Yes.
I still have problems because now I found that RP is still significantly larger than CP.
How much is RP?
What I found, the RP is 2.9936 when the GT is 10 dB.
How much was your the other I need to look at, tell me
That's
your
not
name.
what I got.
Station, I found RP was like 0.54.
I put 0.754 for me.
Yeah,
Yeah.
Yeah,
it's
his
less
radius
than-
didn't change when he changed the GP or the CP. It doesn't depend on that.
No,
Yeah,
exactly.
your
When you
radius shouldn't
change
change, that's
C2,
correct.
yes, it should not change the, so you may want to go back, Jaehin, and check RP. I'll tell you how when I see that. Okay, so here is from experience. When you see a transistor that has a large value for S21, you know it can give easily 10 dBs. When a 3 value of S21, it can easily give 10 dBs. That's how I selected it, and I never thought it was going to be outside, because if it's outside, if it was like the previous example that you saw me, like we'll never get 10 dBs. We'll get 20, we'll get 0.2 dBs, like a ridiculous low gain to be able to cut the Smith chart. But when you see an S21 that is large, usually these transistors give a very good gain. So it has to be inside the Smith chart. I will be totally surprised if it's outside. Now the stability is a different story.
Stability is a different story.
Okay. Let me ask you something else that I wanted to clarify. As I was looking at my notes, I thought, and we have a few more minutes to discuss that. In this particular example, I also gave you a VSWR. Remember to be the input VSWR to be less than 1.5. You remember that, okay? And then when we looked at the VSWR circles, where are somewhere, I don't want to make you dizzy, here, there are both for input and output, obviously. Usually most of the time, well, you never know. A lot of times they will only speak about the input VSWR, but for a low noise amplifier, people may look at the output too. So what is the interesting thing here in this? That you have the circles for the input VSWR that are functions of the gamma in, which is this, and gamma L is a function of gamma S. Now, your VSWR, when I come and say I want a VSWR, which is 1.5, that one is going to fix my gamma sub in A value. All right. And then I still need gamma sub in. And I will still need to go through a relationship like this, which is kind of complex to do on this Smith chart. I mean, you cannot do this on the Smith chart. Practically, what that tells you is that you have to select some values of gamma S. It would be the easiest would be to know the value for gamma S, and then find gamma in. If you knew the value for gamma S here, then you can go and find gamma L there, and then you can go from this, find gamma in there. So practically, if you don't know your gamma S, which happens when you have circles overlapping, like in this case, if I were to remove the VSWR circle, what did I do? There. If I were to remove your VSWR circle and look at this one, let's assume, all right, what I will do is to assume that I have, I need to create an amplifier, and I have found the noise already circles, or I have found my one noise circle that I'm interested in, which is the 1.3 dBs. So I do whatever I have to do there. I will do approximately things. So you find this line. Let me do this well. Let's just, if you find this line, you find their gamma optimum. And then, which is part of, which is given. And then from there, you start building your F circles. And let's assume that I found the 1.5 dB circle, which was somewhere like this. Okay. All of these circles need to be, their centers need to be there. Okay, I found that. Now somebody comes and says, this is your 1.5, 1.5, and then I had also the 2 dBs. I'm not interested, 1.3. If there is anything, I need to be better than 1.5. That's what they told me. So practically, this is my 1.5 dBs. So now somebody said, okay, you're gonna be inside the 1.5. It's inside because this is my gamma optimum. This is the best, this point here, which is called gamma optimum, gives me the lowest noise. So this point here, which is called gamma optimum, is nothing else but your gamma S, which gives you F minimum. All right, so at that point, you know that you have F minimum. Now, I cannot be at that point, obviously, and have a VSWR circle, which is like have a low reflection on my input port. So how am I gonna print this circle? Then I know, before I do that, I know that I need to have a gain. So let's assume that I'm creating the gain circle. And I find, as a matter of fact, that I have a gain circle, which is like this. And let's assume that this gain circle is, oops. This one, let's assume that this is a gain, G sub P. G sub P, it's 10 dBs. That tells me that I have an area here of points, as we discussed last time. I have an area where I can have both better than 10 dBs, and because if you remember, as your circles here become smaller, you go to higher gains. So if this is 10 dBs, this could be, say, for example, 15 dBs, all right, smaller. So I know that I can be higher in this red. I can be higher than 10 dBs and I can be lower than 1.5 dB noise. All right, do you understand what this red region gives me? Is that clear? What this one does for me?
Yes.
It's
Yes,
the region we
yes.
want.
Yes, but now from that region, you want to find the points that give you from this region, from here, you want to find the points that give you VSWR less or equal to 1.5. So now you have to go and put, it's an additional constraint, all right? So now you have to go and put your VSWR circle. So here is how I would do it. I would take few points from there. Like I may take the center point of this region, for example. I can take this point, which is at the center. Center. I can take this and 1 second. Yes, 1 second. Don't know. Okay, then I will take this and from this one, for this point, this is my gamma S point. For this point, I would define all the VSWR circle. So now I can go to the VSWR, which is, I gave it up here. So now I can go here. I have already defined my gamma S is here. Okay, so I put gamma S there. I find gamma L here. I put gamma L here, I find gamma in. And then with gamma in and gamma in alpha that is coming out of the VSWR equals to 1.5, then I can draw this circle here. And this circle, it could be as follows. This circle could, no. This circle could be somewhere here. Oh my. Could be somewhere here. All right. And in that case, are all of these points that are acceptable, all of these points. And from all of these points, I would get something at the center. And why would I get something at the center? Because all of these, is, they are designed for one frequency. And when the frequency changes, I don't want to be myself too close to the perimetry of this shape, because I may find myself totally out of this. So I usually go into the center of what shape you find. Now, this yellow circle, it could be somewhere here. And in that case, you will have a problem, because then if your gain is somewhere above 10 dBs, and if your noise is somewhere below 1.5, then you cannot have a VSWR gain, which is less or equal to 1.5. Okay, so that's what exactly is happening. And you need to keep that in mind. Any questions? I'm gonna solve problems in about half an hour, so we can continue that. But is that clear? How you do the VSWR?
So when we find the VSWR, then the yellow circle is VSWR.
Yes.
Okay. By the way, I've recalculated, I tried to use the new formula to calculate for C and R, but it's still.
Okay, yeah. Well, you look at this carefully to make sure that you have the correct numbers. Okay.
G is 15.
What?
G is 10, right?
Professor, I think you're muted.